Welcome to the Asset Seminar, and today it's my pleasure to introduce Pratik, who is in ESE, and as we were just discussing, we don't get to hear talks from our own faculty, so this is an opportunity to find out what Pratik has been up to, and he's going to talk about learning from small data.
So, thank you everyone for joining. Thank you for the invitation. Very excited about this new center. Let's see. So today I'll tell you a little bit about our attempts to do machine learning when the number of samples that you have to do machine learning is quite small. Of course, something has to give. So you cannot magically start doing machine learning with few samples. So this is so in the next 1 hour, we are going to take a look at different ways of reducing the sample complexity. And as I said very provocatively in my abstract, in machine learning, we've always talked about asymptotic things when the number of samples goes to infinity. Of course, this is not very useful. What we care about is when the number of samples goes to 0. That is really what we want to do as machine learning people. In terms of the organization, I'll tell you a number of examples, and then I'll try to draw some themes across these examples of how sample complexity can be reduced. And then look at 2 specific threads of research that we are working on. Yeah. So all said and done, after about a decade of deep learning, it is fair to say that we are good at solving problems in the high sample regime. We may not understand very well why these methods work, but most of us can build models if we have some data. And roughly speaking, this number could be 100 samples per class, 1,000 samples per class. We are good at these kinds of problems. What we are not so good at is what would we call the low sample regime, where I give you 10 samples per class. And one nice example to keep in mind is imagine that you're a farmer, you grow some strawberries on your farm, and there is 3 kinds of strawberries that you grow, and you would like to build a machine learning algorithm that sorts the strawberries. You don't see why any scientist should need any data to begin with, because you can do it yourself anyway. If you are Google, you don't want to build a model for one particular farmer. You want a model that works for cucumbers. You want another model that works for some other grain, etc. These are all low shot problems because you either don't have too much data from the problem because someone never bothered to collect it, or because you are solving new problems. So when Google wants to do translation in Swahili, there's not that many people that speak Swahili inside Google, so they have to go collect data, or they have to use data from some other languages to be able to adapt to any language. Right? And these are, roughly speaking, small size problems, but they can arise from different kinds of things. The third regime, which we really haven't started talking about yet, is extreme low shot. You see something new, and you really don't know how to understand it. So right now, when we do deep learning or machine learning more generally, the world is partitioned into 1,000 classes, and the model has no understanding of what happens beyond these 1,000 classes. Anomaly detection or extreme low shot learning or open universe style problems fall here. And we haven't really started to talk about these problems yet. I'll primarily be looking at these kinds of things in the talk. Yeah. Let's take a look at how current methods for these problems work, and I'll give you one specific example. This is not a general statement. People work on stuff that is called few shot learning. Few shot means that I give you a few samples from my new classes. So let's say 5 different kinds of strawberries, 1 label sample from each of these classes, and I would like you to make some predictions. Of course, these 5 samples is not very useful to build a model. So what you do is you gather some data from some other classes, related ones, let's say cats and dogs, and try to adapt the features of your model to these new classes. Roughly speaking, these methods work as follows. So they'll take the data and they'll learn to cluster this data, that comes from different cats and different dogs, with the hope that when I show you images from the new classes, the same clustering mechanism is also useful to distinguish between those new classes. So you are solving few shot learning effectively by building a clustering machine using data from related classes. And this is kind of a well-established field right now with many different methods to do this across the years. What I want you to focus upon is when I show you new classes, there is many different kinds of new classes I can show you, 5 strawberries, 5 giraffes, 5 mangoes, etc. Right? And the world is full of diverse tasks like this. The accuracy of the methods that we have built, and this is a box plot with 99 percentile error bars. The average accuracy on a new task goes from 85% to 15%, which is absurd when you think of how you would use these systems in practice. We found this out while writing this paper a couple of years ago. And although people had been developing methods that kind of improve the mean accuracy across all these tasks, the error bars on these mean were so large that all of these methods are perfectly indistinguishable from each other. What I want you to focus on is not the fact that these methods are better or equal than each other, but the fact that there are error bars and the world has many diverse tasks. To be able to say that I do well on all new tasks is not very meaningful. You will always be able to find tasks where you will not do well. Okay. So the name of the game, if you're interested in doing well on new learning tasks or doing well with few samples on new tasks, is to find some common shared structure among tasks that helps you in this process, that reduces the error bars. These error bars are across arbitrary classes. If you restrict only to animals or restrict to only to some kinds of geographic locations, you hope to get more stricter error bars. Yeah. Here is a simple way to think about the problem. I talked about clustering as a way of solving the problem. Let me look at a very simple way. So fundamentally, I give you a data set, and in machine learning, we say I would like to find a function, little f, such that is computed using this data set ds, such that when I plug in a test datum x, I get some outputs. Right? In principle, I can find this function in any which way I want. The only reason we parameterize these functions is so that the process of searching over them becomes more efficient. The weights that you find at the end of training are a statistic of your training data set. They better be a useful statistic of your training data set, useful in the sense that the test datum can be predicted accurately using these weights. But fundamentally, we do it as an engineering exercise of reducing our computational complexity of finding these functions. I am not saying anything very deep here, neither anything controversial. I am just saying it in a peculiar way. I can think about this slightly differently. If I have few samples, it is very hard to find a good statistic of the data set because my data set is fundamentally small. There are many possible weights that I could have used to fit those same few samples. So I'm going to search over the space of functions a little bit more explicit. And here is one objective that you can write. Let us say that I give you NS training samples, and at test time, I force you to make predictions on NT test samples. Okay. In classical inductive inference, you would build a model using the NS training samples and then run this model independently on all the test samples one by one and make those predictions. This is a slightly different objective. It says, give me the weights that you trained on my training samples, W star, and search over some neighborhood of these weights more explicitly that maximizes the likelihood of correct predictions on your training samples. Of course, you don't know the true labels of the test samples. So it's not as if this objective you can write down very nicely. Okay? What do you have to help your case? You know that your new weights may not be very far away from your old weights. W cannot be too far away from W star. And I have some test data points, test inputs to use. So if I minimize this objective, I am updating my model explicitly by looking at a bunch of test inputs, but without knowing their labels, and then finding the most likely outputs that I can get on all these NT samples. This is a slightly different way of thinking. It is called transductive inference. It says, I make predictions not on one sample by itself, but I make predictions on a bunch of samples together. And what helps me make these predictions is the shared commonalities between these samples. Okay? In pictures, it looks like this. So let's say this was our training data set. I fit a max margin SVM to split these points nicely. At test time, I get some unlabeled points in addition to my training points. It may be worth my while to modify my hyperplane to split them like this. Of course, I don't know the labels for these points, so I could be making modifications that are wrong. But most of us will draw a hyperplane like this between these two points. So transductive inference exploits the fact that unlabeled test data can have some structure. That is, if you can relate that structure to the hypothesis that you have created from the training data, then you get to make slightly more accurate predictions. And you can analyze the theory of this, etc., etc. But fundamentally, it's a slightly different way of thinking than inductive inference. Yeah.
So omega here, what omega is going from x over s plus 1, not from x over 1.
I could also do it from x1 to xnt, ns plus nt. But my W star already captured in whichever way W star was created, it already presumably had this. What I want to show is that we have this information and we can use some function omega to exploit this information. Typically, in this particular paper, we were using semi-supervised learning style objectives to exploit this information.
So when you say small data, I should think of the label data going to 0 and the other one be constant.
Yes, yes. So we should always think of the label data going to 0, and then we can either ask our mama to get the predictions or we can get more data from other tasks. So something extra needs to come in if the label data has to go to 0.
So in this picture, what are you trying to optimize? The delta to the your original separator, or the
no,
or the error.
The error. So we don't care how far away we move from the original hypothesis. We may not want to move too far away. That is true. But fundamentally want to minimize the error. So whereas the joint likelihood of all the labels of the new test samples. So this is a very complicated way of saying that I fine tune using my samples, but fine tune using the inputs, not just the outputs. Yeah. So you don't want to read this table, but in the tradition of all the empirical papers, you will notice that one of these lines is bold throughout. And what I want to say is that there are many methods to do few shot learning, to do well on new classes with few samples. If you simply do transductive fine-tuning, I take a model, train it on my source samples from other classes, and when you give me new data, the few samples from new classes, I simply fine-tune the model, either using the test data that I test inputs or using the few label data of the new class. You trivially get way better performance than all existing methods. This was true a couple of years ago. This method right now is used by basically every few shot learning algorithm out there. We started doing it for images around 2019. Yeah. Yeah.
So this is fine tuning with training where you're updating the weights.
Yeah.
So where does the models that you're updating and these kinds of things where you give information or extra few shots like in the form of non-training? What does that lie?
Yeah, so the way we do prompt, the way we use prompts for getting inference out of language models, it's a little bit closer to latent model or using the way distribution of the latent variables and then conditioning on different parts of it than explicitly updating the weights like this. So I would formalize it if pressed to do so, still using transductive inference. But the weights won't be updated. It will be the a distribution of the joint limits.
I am a little bit confused. So in transductive fine-tuning, so I don't have the omega star. So in practice, what am I actually optimizing?
Transductive learning, you do have the omega star from the old data. The cats and dogs give you W star. The strawberries are your samples NS plus 1 to NT.
So omega star is a pre-trained network.
You take a pre-trained network. Now you adapt this network. Someone gives you some labeled data from the new classes and maybe some unlabeled data for the test queries of these new classes, and use all of that to adapt. The key point is adaptation. Yes.
How does it vary for n equal to 1? Are you always presented?
Yes, for n equal to 1, you shouldn't be doing this. We should be doing inductive inference because there is nothing that we can learn from this one sample, or at least like we may be wrong when we adapt.
If you have an assumption of like how large n should be, so my actual question is how does it vary?
Yeah, so you can write down like uniform convergence bounds for transductive inference also, and you will see such patterns emerge. Specifically, it is about reducing the VC term. The square root term of course doesn't change. Okay, so one example of where adaptation works effectively, even if you have very few samples. So one sample per class. Okay. Back then, like this was the first experiment to be done on the large ImageNet. Large ImageNet has about 22,000 classes, 31,800, and 14 million images. And so what I did is I took the first 7,000 or so classes, which have lots of images per class, and called them my training data set, the NS part. And then I took the new classes, these about 13,000 classes or so, which have few images per class, and said that my new tasks are going to be coming from these classes. It is pretty surprising to notice that one shot, so one sample from 5-way classes, so 5 new classes, you can predict accurately for 90% of the images. Okay, and this is pretty shocking. The only reason why this can be true is if these classes are really not that different from each other. There have to be some very strong shared properties across these classes, and that is why we can get such high accuracies on new classes. Cool. So how does a small sample size show up in clinical data? So this is a thread of work that we have been pushing on. Let us take the example of Alzheimer's disease. So we have, one of the students in my group is working with this professor Christos Davadzikos in the radiology department on these problems. For something like Alzheimer's, you have pathologies that are quite different. There is plaque formation in the brain that can cause you to have dementia. And different people have different rates of growth of plaque. Different people have different kinds of plaque also. Some people have amyloid, some people have tau that grows. Now, the key thing to understand is that before these symptoms, plaque formation, for instance, can begin almost a decade before you show any symptoms of dementia. Okay, so and this is of course very different for different people. There is many different mutations that are related to the amyloid pathway. So some people have this one, some other people have this one. Out of these 20, about 1 or 2 of them are pretty common. The others are very, very rare. So less than 1% of the population has these things. These are all like looking like low shot problems now. Aging, of course, is quite different for different people. So different brains age differently. And when they look at the shape of the brain and say this brain has atrophied versus this brain has not atrophied, you can make mistakes because of the rate of changes in different people's brains. Okay. These are the biological causes of variability in the data or heterogeneity in the data. There is also more silly ones like this hospital likes this particular scanner, that clinician likes that particular setting on the scanner, and our data sets in clinical world are created by combination of such desires and such choices. They are obviously heterogeneous because of the biology, but they're also heterogeneous because of these more operational aspects. And you will also notice that typically women or racial minorities, they do not like to take part in clinical trials. So we have much fewer data points for racial minorities. Now, all of these are like well-studied problems for Alzheimer's disease even specifically. All of these translates to small sample sizes. There is no such thing as one canonical subject. The hallmark of clinical problems is that every subject is quite different from one another. And machine learning fundamentally is about finding salient things in lots of data and then using those salient things to make predictions. If you have data that is not salient or that has a lot of heterogeneity, then you are fundamentally fighting salience. So you would like to add more explicit ways of addressing the heterogeneity. And what we have been working on are ways to go beyond building just invariants to this heterogeneity, which is what you will see as being done in a lot of places, or it is kind of a first thing to do. If the heterogeneity is very large, then it pays to adapt to that heterogeneity more specifically instead of being invariant. And that is the kind of argument that I will make in the next few slides. This is work by Rong Wong, who is a student in ESC, co-advised by me and Christos. Let's see. So let's first see how to address heterogeneity by being invariant to it. The reason we want to be invariant is we want to find only the salient features and force ourselves to not focus too much on the non-salient parts. Okay, there are many ways of doing this. All the way from modern machine learning, things like invariant risk minimization, to older stuff like harmonization before you make the predictor, etc. Here is one recent result that we found. So we took data from pertaining to subjects with Alzheimer's disease from these very large data sets that have been collected at Civica and also the rest of the world. We used features that people typically create from these images. So these are three-dimensional MRI images. And what they do is they parcellate the brain in different regions, and they record the volume of the white matter or gray matter in different regions, and that becomes kind of a feature vector. So in this case, it was about 150 different regions in which the brain was parcellated. In addition to these features, we also had stuff like some genomic readings, so different alleles that are present in the subjects, some clinical markers like hypertension or diabetes, and etc. And of course, demographic information, so male, female, age, group, etc. And using all these features from many different clinical studies, so ADNI1, ADNI2, Penn, ABLE are all different clinical studies that have collected such data. We were interested in understanding the following question. Can we build a model that can predict uniformly across all this diversity? There is diversity in terms of gender, there is diversity in terms of age groups, and notice that all of these are rather unbalanced across these different groups. And in this particular paper, what we showed is that if you do pre-processing right, by pre-processing, I mean good old-fashioned pre-processing, quantile normalization of the features, throwing away features that have too much entropy, or imputation for missing features in reasonable ways. So simply do good pre-processing on your inner features, then statistically, there is no perceptible bias across all these groups. So this is, here I'm writing in the p-value for the accuracy on females being higher than the accuracy of males or not being equal to be more precise. And so in this paper, we did these kinds of studies for three neurological disorders, Alzheimer's, schizophrenia, and autism. This is just a classification model, so nothing very complicated than that. But the point that I wanted to make is when we look at clinical data, we know that it is heterogeneous. It is heterogeneous, it is very imbalanced and stuff, but that doesn't mean that we will always get biased predictions. Oftentimes, when you see papers saying biased predictions, they are kind of skirting around like well-established methods for in the machine learning literature to get good generalization. And if you simply do things in the textbook way, religiously, then at least in these three examples, we did not notice any bias. Yeah, yes.
Minor question, so what the race doesn't have?
Yes, so yeah, so there is some missing stuff that we don't know the rates for. So there are some subjects for which we don't know the rates.
Yes,
Yeah, we didn't put it as a yeah. Yeah, so the point of this question is not to say that machine learning models are not biased. They can be biased, but this is evidence from three particular examples that they don't have to be biased if you do things properly. If you don't do things properly, then yes, they can be biased, but then that is not the right way to do it anyway. Okay. So that is invariance. If you have very high heterogeneity, then it stands to reason that being at the average of these features is not going to help you. So being invariant is necessarily plucking out the worst feature that is in all your groups, right? The stuff that is the most shared. If the stuff that is not shared is very large in its information content, then you cannot get good predictive performance. So the next way or to address larger amounts of heterogeneity, larger degrees of heterogeneity, you want to build methods that can adapt to this. Okay. And so here is one example. So this is again Alzheimer's disease classification, control versus dementia. And these are a few different clinical studies in this case. So OASIS is the one that is new from the previous slide. And these are collected from across the world with very large degrees of variability within each of them also and across them also. And what I'm showing you here is a neural network that was trained on ADNI1 gets 86% accuracy on ADNI1. Okay. The same network without any extra data, when I run it on ADNI2, it gets 82% accuracy. So that tells you that there is some difference between ADNI1 and ADNI2. So in this entire matrix, the row consists of what was used to train the model. The columns consist of what was used to evaluate the model. And you will see that clearly these data sets are quite diverse. Your model drops a lot in its accuracy. If you do pre-processing properly, and if you do just a weighted ERM with a few samples from one of the columns, then you basically kill all the red cells in this matrix. Okay, so this accuracy was 82% without using any data from ADNI2. If I do pre-processing properly, then that number is about 86 or so. And if I have about 10% data from ADNI2, then I get 90% predictive accuracy on ADNI2. And this is the theme for the rest of the matrix also. So what I want to convince you of is that you can address heterogeneity by being invariant to it. In most cases, you will do very well. The reason in the previous slide we are doing much better than existing work is because we are using the features in clever ways. The one irony, I guess, let's see if people in this room agree with me, is the medical imaging world or neuroimaging world, to be specific. They got very tempted by deep learning, and then they started using all the deep learning based methods, but their older stuff is much nicer. You can use the pre-created feature, structural features that people have created in these fields. And if you do machine learning right with them without even using neural networks, so this image is not using any neural networks. It is just using an ensemble of random forests. And so you will get much nicer answers. So using images is tempting, but it is very difficult. Whereas these older features that have been created in these fields are very powerful. Here we do adaptation, not by fine-tuning a learned network, but by just weighted empirical risk minimization, using some samples from the source side and some samples from the target side. This is nice because it is oblivious to the specific architecture that you are using. You can also do this for random forest, which is exactly what this particular result is. Yeah. Sometimes you may not have labels of the target study. So, and this is the more common problem. So you build a model using Penn's data, you go to Harvard. Harvard is not going to give you labels of their samples. So you cannot adapt the model to that data. But in a lot of cases, you can have some auxiliary tasks that are related to your task. So for instance, age prediction is something that many people will be happy to give you data for, even if they don't actually give you the labels of dementia versus non-dementia. So you can use this task to adapt to new data. At the end of the day, we want something that is correlated to the target task. If it is age, we are fine. So in this case, we are adapting to subjects, let's say in age group 60, below 60. So 60 is actually, you don't see too many subjects, so there's a very small sample size in Alzheimer's. So, but let us look at this one. The green is what you get when you train on one source site. If I give you data from the target site without actually giving you the labels of dementia, but simply the age, by regressing on the age, you can improve your performance for predicting dementia. This is another way of adapting. Why does this work? It works because there has to be, again, some shared structure among the tasks.
Sorry, I don't. What do you mean that you get data for it? I thought, I mean, how is it different than adding that as a feature? You're trying to predict the disease, right?
Yes, we are trying to predict dementia versus not dementia. Yeah. And now we have inputs from a slightly different distribution. For these inputs, we may not have labels of dementia specifically, but we may know the age. Now you're right that it is not that different from adding age as a feature. This particular image, to be specific, was using images, not the tabular features. But it did not have age as an input feature, but it is regressing age on the output, but similar features.
What are the values in the first?
Those are test standard deviations. And the ones on the diagonal are 0 because basically we look at, we do like a nested 5-fold CV. So this 86 is the mean of multiple test folds of that particular result. So there is no standard.
And these are like neural networks. So basically, you have to.
This one, yeah, this is a neural network, and then this is actually a ensemble of random forest.
So yeah, I guess if you have the new data for one of the neural networks, and you're trying to update the first based on the changes that you see
in the distribution. Yes. So every in this particular matrix, we are not updating. We are simply doing weighted ERN. So you fit a new model to all your existing data and 10% of your column data. Here there is no adaptation whatsoever. This is simply evaluation on the column. So this is kind of the baseline that you would get. This is what you buy by the 10% extra data.
So on the diagonal on the right, the value, I should think of the values being the same as the left.
Yes, they are predictive accuracies. Yes.
But
the right hand side has more information than the left hand side.
Like on the diagonal, my point is, why is the diagonal?
Oh, diagonal is the same, right?
Why?
Because I don't have any extra data on the diagonal. It's the same site.
I see. Yeah.
So you mentioned that this has the benefit from the shared structure task. That I'm going to
Second part of it. Okay, coming there.
more stories.
And I have a question. The matrix on the right should be symmetric, right? Because if you're doing weighted ERM alpha and 1 minus alpha,
The alpha is different.
but if I plug in 1 minus alpha on the other one, I should get the one on the other side, right?
No, because the goal is to get good performance on the columns. So the alpha is chosen. So this is actually, there is some theory behind this. The alpha that is chosen is to get good performance on the columns. Essentially, it should not be simple. Okay, so the question that until now I have shown you many examples from my work. There are many other examples in the rest of the literature that adaptation somehow works very well. Adaptation is useful to do when you have heterogeneity in the data, and in some sense it is a very nice and simple way to address the heterogeneity if you have some sample size or some auxiliary tasks. Why does adaptation work well? Of course, it can only work well if there is some shared structure among the tasks, like you said. And so this is a big line of work that we are doing in my group on understanding the geometric structure on the space of learning tasks. And I would like to say these two tasks are close to each other. These two tasks are far away from each other. So fine tuning on the one task that is far away from your source task is difficult, or fine tuning to nearby tasks is easy. These kind of statements I would like to make rigorously. Okay. Let me tell you why not all tasks are close to each other, or when fine tuning does not work. Okay. And I'll use the information bottleneck principle as a way to think about this. So the IB is a kind of a idea that is a generalization of rate distortion theory. It came around in the late 90s, and it goes as follows. So imagine that I have inputs X and I have outputs Y, and I'm building some representation of my inputs Z. I would like this Z to be capable of predicting Y. Otherwise, I shouldn't be building that Z. Right? So what kind of Z's do we like? We like Z's that are sufficient to predict the target Y. I should not be able to not predict. Between two Z's that are both sufficient, I like Z's that are somehow small. Why? Because it reduces the amount of storage that I need, or it reduces the amount of information Z carries with X. Yeah? If both of them are the same rate accuracy, then I like to throw away part of the image X when I create a representation. One way to formalize these kinds of desires is using an objective like this. So I denotes the mutual information, Z and Y are random variables. I would like to maximize the mutual information between the representation and Y, and I would like to minimize the mutual information between my X and my Z. The first one forces Z to throw away lots of information about X, but the second one tells you that don't throw away anything that you will need to make predictions about Y. This is not the only way to formalize this, but this is one nice way to think about what kind of representations we learn. Okay. Now, if you follow my chain of thought, Z is trying to predict Y, and Z throws away everything about X. But when I go to a new task, everything that I threw away from my source task is exactly the stuff that I need for my target task. This is a very simple point, but a very important point to understand. I am solving one task. I go to another task with my same representation. If I threw away stuff from my source task, if the target task was even a tiny bit different from my source task, then what is noise for the source task is signal for the target task. If this is not the case, then the two tasks are the same, right? So if you believe me that information bottleneck is a reasonable way to think about representation learning, then fundamentally it doesn't work when we move the model or the representation to a new task. We already threw everything away, so we should not be doing well on new tasks. The only way we can do well on new task is if it is a damn subset of the old task, which would not be very interesting. So let's ask a slightly different question, and we have like some papers on how to not throw away too much information, but I'll talk about a different work. When is adaptation effective? We know that it cannot always be effective. So let us try to understand when it is effective. So this is work by Yansong Gao, who is graduating this year. So if you have, if you hear about jobs, let me know. He has some very nice work on understanding the space of tasks. What we wanted to do was characterize a notion of a distance in the space of tasks. And when I say a task, to me, a task is a joint distribution of X and Y, inputs and outputs. And I would like to say, give me some notion of the distance between two such joint distributions. There are many notions of distances between joint distributions, but they are not learning tasks. They are just notions of distances between distributions. Right? We would like some notion of distance that understands the capacity of the model that you're fitting. If you fit a very large model on a task, on two very different tasks, you can fit both of them pretty fine because the large model has a large capacity to fit good tasks. If you fit a small model to one task, then presumably adapting the small model should be much more complicated or much harder. So the capacity of the hypothesis space that we are using to model our task has to play a role in two tasks being far away or two tasks being nearby. Make sense? Okay. So large models we know can fit many things. So all tasks should come close by for large models. One more thing that I wanted to do was you will see a lot of work trying to understand distances between learning problems, between normal estimation and image segmentation, between cats and dogs and mangoes and strawberries, etc. The way people typically think about this is I train a model on cats and dogs. I count the number of epochs that it takes me to fit mangoes versus strawberries. And if I take many epochs to fit the new task, then presumably these tasks are far away from each other. This is not a very satisfactory way of quantifying the distance between tasks because it depends on how I train. I would like a definition of a distance that is oblivious to how I train. It only understands the distributions and the hypothesis space. Okay. In particular, we were after some notion of an optimal distance between learning tasks. Now, if you kind of, you may complain that if you're inventing a distance, then there is no such thing as a unique distance even. So clearly there should be no such thing as an optimal distance. So I will define what notion of optimality I care for, and we'll talk about those kinds of distances. Yeah, here is one way to think about this. So let us say that we have a source task, training data set. We fit in a model on this, and let us say that the weights of that model are WS. A model at the end of the day is a distribution y given x. Give me x, I predict different y's. This is the input marginal PS of x on the source given. So think of this as cats and dogs. I am interested in adapting this model to a new task, mangoes versus strawberries. This is PT. I am after finding this new weight WT. Okay. When you do fine tuning today, what you do is you take this particular model and start fitting it on the samples from the new task. And now the model can take whichever trajectory it takes to reach WT. You select the WT that you want at the end of your 100 epochs and you call it your solution. We would like to do things a little bit differently. As you can, if you can imagine that if I don't show PT directly, but if I show you some interpolated version of PT, then the model will have an easier time tracking this distribution. It is like saying, I want you to go to that place, but I don't tell you how. So you're going to meander your way around to that goal. But if I show you something more gradual or something that changes more gradually, then I can keep track of how you're moving. Right? There is a reason we meet graduate students for the first 5 years of their PhD and not simply tell them to write a thesis after they start. So we are interested in finding interpolating distributions across the two learning tasks. The trajectory that a model takes by tracking these distributions is what we will say is the distance between two tasks. Okay. You want the trajectory to track the way the task is evolving, and you also want to evolve the task in a way that the trajectory is evolving. So the task should slow down, roughly speaking, if the models are finding it difficult to track a particular trajectory. Okay. This is a joint optimization problem that you can formalize. And the formalization goes as follows. So I know that it is 15 minutes to the hour. So I will give you the short version of this. This is a little pesky mathematically. We think of probabilistic models using some ideas in information geometry. So every distribution is parameterized by some weights W, and there's a manifold of such distributions. Every point on the manifold, you can think of it as W being the coordinates of this manifold. Okay? This is something called a statistical. On this manifold, you can use any which divergence you want to impose some Riemannian structure. So the Keil divergence is the Keil divergence that you know. It is the distance between two distributions. That induces a metric on this manifold. That tells you that 2 points on this manifold are nearby or far away from each other, in which directions the distances increases quickly, in which other directions the distances increase slowly, etc. Yeah.
But the Keil is symmetric.
But you can still define distances. So you can still define a metric using even for asymmetric divergence. In words, what this means is that an infinitesimal length on the manifold ds square, which is the distance between PW and PW plus DW, infinitesimal changes to my weights, is given by some quadratic form where the matrix inside the quadratic form is the metric of the manifold. It is called the Fisher information matrix. So the eigenvectors of G that correspond to large eigenvalues are directions in which the distributions change quickly if I perturb the weights, and the eigenvectors corresponding to small eigenvalues are directions in which I can change the weights a lot but not change the distribution too much. Yeah. A notion of a metric on this manifold is what is called the Fisher-Rao distance. The Fisher-Rao distance is the shortest trajectory joining two points, W and W prime. There is a manifold, think of it as a sphere, and I am drawing lines on the sphere. The line joining two points on the sphere is what? The circle.
Geodesic.
Yeah, the geodesic along the sphere. And so for the case of a sphere, it's the great circle, right? So the Fisher-Rao distance is simply the length of the great circle arc that joins between these 2 points. If your manifold is a circle, in general, it is the length of the trajectory. So it is the integral of ds. It's the square root of w dot g times that. Yes. So
I want to pick up on the question. So essentially, the distance, because this g depends on the first probability, the metric. So the metric of the manifold depends on the first probability that you consider.
no. The metric of the manifold is a local quantity. It does not. It only depends on the
On
local
the manifold itself. Okay. So then, how is it? Sorry. So how is it that the scale divergence is not symmetric, and then you transform this through the manifold into something that is actually symmetric?
The Fisher information matrix is symmetric. Yes, the scale divergence not being symmetric is not a problem because PW given DW. So different directions. So the metric of the manifold is different from the connection of the manifold. So I think they don't have to be, the metric does not have to be the same across 2 points. The connection is the one that tells you how the metric moves.
And so the manifold is defined according to EX.
It is defined, it is a manifold for every X. So there is for every input X. So it is a manifold of outputs Y. This is a distribution over all possible outputs, right? 10 classes, if you want to talk of 10 classes, it's a 10-dimensional manifold. And we are simply writing down some formulae that impose a Riemann structure on that. Okay. When you want to think of transporting the task, there is many ways to do this. You can think of linear maps that take your empirical distribution of the source task and the empirical distribution of the target task and connect them. So you take all your input images and your output images. This is a linear map that tells you how to go from one input image to an output image. The map that we like the best is the one that forces the weights to travel in a small trajectory while tracking these interpolations. Okay. Interpolated distributions can be calculated using something called as displacement interpolation. This is one specific way to do displacement interpolation, but roughly speaking, it takes the convex combination of 2 distributions, and there are many ways to do this. We can worry about them later. Yeah, let me show you how it looks. So this is the length of the trajectory that my weights are taking. This is simply gradient descent that I am doing on the weights to track these interpolating distributions. The interpolating distributions are a function of the gammas that I'm calculating, or the couplings between 2 tasks that I'm calculating. And the couplings that I like are the ones that cause the weights to take a small trajectory. So I have 2 distributions, the source and the target. I define a coupling between them, a linear map that takes inputs from one to inputs of the other. The map is such that it lets the weights travel along a small trajectory. The weights travel along a trajectory that makes the model break well along all interpolations of this map. This is a joint optimization problem where you update the map and the weights. And you can argue that this is the shortest trajectory that the model has to move between two tasks. The cool thing about this is it's a very heavy thing mathematically, and there is a gaps here that some of you might see. But one cool thing that you can say using this is if you have a model that achieved 95% accuracy on a source task, and I have a new target task, I can guarantee you that you will always also obtain 95% accuracy on the target task if you run this process. It is a completely controllable way of doing transfer that guarantees the outcome that you get. Right now, there is nothing that comes even remotely close. Right now, you just fit on the target task and you accept whatever accuracy you get. This is a completely controllable way of doing this. Executing the process becomes harder and harder when tasks are far away from each other. So you cannot win all the time, but mathematically, it will give you the classification error that you want, if it is achievable by that hypothesis class. Okay, it's a very weird way of doing transfer because it also interpolates the data. Typically in transfer, we actually only show the target data. Let me not worry about these experiments. Yeah.
Like, why does the path the model take matter for the performance of the final? Because you get to the same, you're not always like the schedule model.
The path that the model takes does not matter for the answer. It matters simply to get the distance between the tasks. So we define the distance as the Riemann length of the path that the model takes. The outcome, you are right, that it doesn't matter. I can go there along a long path if I reach the same point. And just
go on a long path, you get there slower.
The Riemann length is larger, yes.
But like in terms of the accuracy of your final.
The accuracy will be the same if you reach the same point.
Right.
I was interested in calculating the distance between tasks. If you don't care about the distance, but you only want the final answer, then you can also go along the longer path. My method gives you the shorter path and the outcome at this particular point of time.
But I could take a different path as long as I get.
Yes, as long as you get it. There can be different paths on the manifold that are not geodesics. The geodesic is the shortest.
I don't want to get into questions of a bit. Intuitively, if two tasks have support on different places, does your method still work?
No, not really. Yeah, so the domain has to be the same. But that's not very difficult to engineer. So you can just add some stuff to the distribution on the tail.
Pratik?
Yeah.
So yes, so I think it was clear to me the last question that you do need the same support because you're comparing effectively P of Y given X for the same set of for the same X in a sense. The next question though is that it can be the case that a task is a subset of another task.
Mm-hmm.
In which case the distance should be 0.
Yes.
In which I think translates to the question of everything is fine when we just think about generic probability distributions, but when the probability distribution lives in submanifolds, then you want to make sure that these tasks live in the same manifold, because if one is a submanifold of the other, then I think you might be in trouble, no?
No, so if one task is a submanifold of the other task, then you're still in business because you will simply travel on the intersection of the two manifolds for the trajectory. So this we can do.
I'm not so sure how. Let me give you a counter example. So when we worked on building distances between linear dynamical systems, then the question of is the order of the dynamical systems the same or not? And if one of them has an order that is larger than the other, then it may be the case that the smaller dynamical system is a subset of the other. And so the distance is 0 because one is contained in the other.
Yeah, so you should get the distance between two subtasks as 0, right? even in my case, if you take a subtask with only 2 classes as opposed to 10 classes, the distance will be 0 because the model will, or distance will be very small. Because the model will only use.
Exactly. I think that's a great example. A task with 2 classes and then a task with 10 classes that include the same 2 classes. Yeah.
So we have done such experiments and we see that the distances are very small. In fact, you can also do like, you can also go from a small task to a big task. You have to be a little clever in creating the output of the model to be slightly different dimensionality.
Yeah, but my point was that it's not a distance, because if the distance is 0, it doesn't mean that the tasks are the same.
The distance is not 0. Actually, it will be very small. Because I can still, simply speaking, I take a model on CIFAR 10, and now I tell you to fit it again on only 2 classes of CIFAR 10. You can change the model a tiny bit to improve your performance on the 2 classes. So the distance is not 0. It is pretty close to 0. I agree with that. If the models, if the models had infinite capacity, it would be, I think. Yeah, so I think it is consistent with this picture. If WS itself predicts pretty fine on this one, then the trajectory will be exactly 0 if it predicts perfectly. So if you're talking about reaching one point on the manifold of the target task, then if you're already at that point, you will not move. If you're close to that point, you move a tiny bit. Make sense?
Thanks. Yes.
It is the end. I want to, if I can, I want to show you one a very cute experiment. I will not tell you the design, but I'll just tell you the experiment. So in a recent paper, we were interested in understanding ways to make the optimal use of data. I'm not satisfied with just using data anymore. I want to make sure that I optimally use any data you give me, whether it is labeled, doesn't matter, whether it is unlabeled, and doesn't matter. I want to find the optimal ways of doing this. So let me show you an experiment. Let's say I give you a biased coin, and I would like you to estimate the bias of this coin. If you're a Bayesian, you can put a probability, a prior from 0 to 1, a uniform prior, and start tossing the coin. After many tosses, the posterior of your bias will shrink, and you will get the true bias. Right? Now, fundamentally, you require a lot of coin tosses because you're putting a prior on a lot of models. If I were to change the question and say that you're only allowed one coin toss to estimate the bias of this coin, what prior would you pick? I give you one bit of information in my one coin toss. So you're only allowed to pick a prior that can distinguish between 2 models. In this case, you would be wise to pick a prior that has half probability on 0 and half probability on 1. Because those are, you only have 2 models. You might as well choose the most diverse models from the space of models and put your prior there. As soon as you toss your coin, it either comes out heads or tails, and boom, your prior posterior collapses to one of these values. And these kinds of priors are called reference priors. So this is a reference prior that is half probability on 0 and 1. And they're a very beautiful way of selecting a prior that depends on the nature of your hypothesis class and the number of samples you will get to make inference. Instead of doing it classically in machine learning, where we say, if I have few samples to choose from, I choose a small hypothesis class. I'm kind of changing the game and saying, I'll still use a very complicated hypothesis class. I'll just use fewer models from that complicated hypothesis class. So I'm not choosing a linear model versus a nonlinear model. I'm still using a very large nonlinear model. I just select fewer ones out of that. Okay. So this is a very old concept in statistics. It is called a reference prior. And so we recently started playing with this. It's a very beautiful formalization for how to make optimal use of all available data. I will stop here because not finish everything, But really, like, I think the last 10 years, we got very lucky. We collected a bunch of data and we also got good answers with that data. Next 10 years, we want to do more ambitious problems, personalized medicine or personalized predictions, even on Google. These are all small data problems. We will not get lucky in these problems simply by collecting data because there is no data to collect. There is two ways to solve these kinds of problems. Either use data from related tasks, in which case you need to understand the relationship between tasks, or you use unlabeled data, in which case you need to come up with clever ways of selecting the hypothesis spaces that let you make maximum use of this unlabeled data. But, thank you. I'll stop.